Oh, I think I'm live. Hello. What's good, everyone? Um, Let me open the chat on my phone. Um, One moment, please. Hello, welcome, welcome. Alright. Okay. So today we're gonna be reading this. Well, we're not gonna be reading the whole thing because it's 200 pages long. But I was thinking of going through this, like the first, chapter or so, or whatever, however long we want, really, of this book, Mathematics Made Difficult by Carl E. Linderholm. Um, oh, sorry, I just realized I'm not sharing my screen. Um, Let me do that. All right, let me get out of the way. All right, so yeah, so this book is by Carl E. Linderholm, or however you pronounce the name. And it's quite an old book. I think it's, yeah, as you can see, it's from 1972. And I thought, this book sounds quite fun. And I've had this book, a PDF of this book for quite a while. So I thought, since it's not too dense or serious, I thought maybe we could go through it together. And if you enjoy the stream, we can go through like the next chapter or whatever in another stream. Um, so yeah, I guess we can just make a start. I guess we can have a look at the table of contents first. I'm just gonna plug in my pen to the computer so that I can write, um, just in case I want to make any notes. Hello to I'm having a look at the chat as well. Hello to Laura A. Could not scroll past that thumbnail. Good luck to you today, Mr. Gregorius Mats. Thank you. Thank you very much. I'm glad that you enjoyed the thumbnail. That one's actually one of my creations. So I'm glad that you enjoyed it. Hello to Copyright. I saw that you were meaning to read this book anyway. So yeah, all right. So let's have a look at the table of contents. So I guess the guy is telling us how to read the book. We might as well read that. First things first. And then he talks about arithmetic, first of all. Something to do with counting, ad astra per aspirin. Okay, I'm not sure what that means. Subtraction, the negative positive diathesis. Okay, multiplication and division and casting out nine. So we're going to be making all of this difficult, apparently. Then we talk about, so once we've mastered arithmetic, we'll talk about factors and fractions, apparently. Algebra. Okay, we're getting a bit technical now. Algebra. What are brackets? Interesting. The incommensurable of the incommensurable, the inconstructible of the inconstructible. Okay, we'll get into that at some point, hopefully. And then finally, we end with topology and geometry. So, and there's exercises. Okay, interesting. So yeah, I guess we might as well just start today by going through the introduction and as much of the arithmetic section as, as we like, basically. So, all right, let's have a look and see what he says. Okay, let's have a look. Okay, so this is his introduction to Mathematics Made Difficult. One of the great Zen masters had an eager disciple who never lost an opportunity to catch whatever pearls of wisdom might drop from the master's lips, and who followed him about constantly. One day, deferentially opening an iron gate for the old man, the disciple asked, "How may I attain enlightenment?" Okay, and the ancient sage deftly caused the heavy gate to shut on the pupil's leg, breaking it. Okay, interesting. So the guy asked him, "How can I attain enlightenment?" And then the master says, he doesn't even say anything, he just shuts the gate on his leg and breaks it. Okay, interesting. When the reader has understood this little story, then he'll understand the purpose of this book. Okay, so my thoughts on this story are, so I guess I don't even understand it. Maybe I'm just not. Maybe what? Anyone got any thoughts on this story that Mr. Linderholm has opened his book with? I assume the breaking of the leg corresponds to like making easy things difficult. So maybe it's like when you try to walk without your legs, you realize how important your legs are, or something like that. And in the same way, when you make maths difficult, you appreciate the beauty, or something like that. I don't know if that's a good interpretation. But yeah, maybe good thing the ancient sage didn't overreact. That's a funny comment. Yeah. Okay. Anyway, it would seem to the unenlightened as though the master had left his student more perplexed by this cool trick. But to the enlightened, this anecdote expresses a deep truth. Um, it is impossible to spell out for the reader what this truth is. He can only be referred to the anecdote. Okay. Okay. So we really got to keep this anecdote in mind then, I guess. Um, all right, okay. Simplicity is relative. To the great majority of mankind, mathematical ignoramuses, it is a simple fact that, for instance, 17 squared is 289. Okay, I mean, I agree, that's quite a simple fact, you know? Maybe I'm just a mathematical ignoramus. And a complicated one that in a principal ideal ring, a finite subset of a set E suffices to generate the ideal generated by E. Yeah, okay, that is quite complicated. For the reader, and for others among a select few, the reverse is the case. Okay, interesting. So we're gonna become so cracks that maybe it's like a horseshoe. Once you're like really cracked, once you've attained enlightenment, once you've broken your own leg, so to speak, it's just trivial that like a principal ideal ring for a finite subset of a set E suffices to generate the ideal generated by E, right? That's just trivial. However, maybe the horseshoe like bends around and we just like start thinking so deeply about 17 times 17 that it just becomes highly non-trivial. Let's see. Um, One needs to be reminded of this fact, especially as applies to mathematics. Thus, the title of this book might equally well have been Mathematics Made Simple. Okay. Whereas most books with that title might equally well have been called Mathematics Made Complicated. So okay, I guess simplicity being relative, that's fair enough. I think that's fair. Um, I like that. I like that he uses the word ignoramus. I like that word. There is no doubt that an absolute ignoramus, not a mere qualified ignoramus like the author, may become slightly confused on reading this book. Okay, all right. So we've been warned. Okay, is this bad? On the contrary, it's highly desirable. Mathematicians always strive to confuse their audiences. Where there is no confusion, there is no prestige. Interesting. I disagree. I mean, I'm not a mathematician, but as a maths enthusiast, maybe I'm an absolute ignoramus still. I'm not a qualified ignoramus. I feel like I want to try and make maths as uh, understandable as possible, but maybe not. I don't know. I guess where there is no confusion, there is no prestige. I guess that is kind of true. Maybe I could sort of see that. Um, I guess mathematics is prestidigitation. What? Okay, what does that word mean? Hold on, I don't know what this word means. Um, the skillful execution of magic tricks. Okay, so mathematics is just magic tricks. That okay, fair enough. Confusion itself may be taken as the guiding principle in what is done here, if there is a principle. Okay, here he's about to explain. Let's have a look. Let's become enlightened. Just as the fractured leg confused the Zen disciple, it is hoped that this book may confuse some uninitiated reader, and so put him on the road to enlightenment, limping along to mathematical satori. I guess that's like a Zen concept or something. Um, If confusion is the first principle here, beside it and ancillary to it is second, pain. Okay. Okay. So basically this guy is telling us, when you read this book, I'm going to try and break your legs, but like mathematically speaking. So he wants us to be confused, he wants us to feel pain, and thus we're going to attain enlightenment. Okay. All right. Okay, that's noted. Hello, by the way, hello in the chat to Zafab and Naman. Sir or brother or better bro, whatever, I don't mind. Bro is fine. Bro is fine. Okay. Pleasure, we take it, is for the initiated. For the ignoramus, if not precisely pain, then at least a kind of generalized Schmerz, which is a German word, I think, which means pain. What is this book about? It's about, well, we're getting an introduction here. Basically, the author wants to take basic concepts and make them in maths and make them complicated. So we're going to be going through the first chapter, or at least the first part of the first chapter, where he's going to talk about arithmetic. But we're just reading the introduction to see what's going on here. All right, well, what's the structure of the book? Okay, let's have a look at what the structure of the book is. Okay. It is a naive account which is hoped to be of use to the reader. The book is divided into chapters, which is divided into sections, which is divided into paragraph, which is divided into sentence, which is divided into words. Okay, which are divided into letters. Okay. For reference purposes, each letter in the book has a number, actually a finite sequence of positive integers attached to it. Okay. Okay. The finite sequence has exactly 6, the first perfect number, terms, so that the book, considered as a finite sequence of letters, is mapped to n0. The natural numbers. The product of the, like, n6, as in like, yeah, you know what I mean, with 0 included. Okay. It has been found very convenient both for author and reader to do this abstractly rather than concretely. Okay, so immediately in this description, he's already complicating things. This book is divided into chapters, and then he goes all the way down to, this book is divided into letters, and each letter has a number, a finite sequence of positive integers attached to it. I mean, okay. All right. Okay. Walking home along a deserted street late at night, the reader may imagine himself to feel in the small of his back a cold, hard object, and to hear the words spoken. Okay, easy now. This is a stick up. Hand over your money. Okay. What does the reader do? He attempts to generate the utterance. He says to himself, now if I was standing behind someone holding a cold, hard object against his back, what would make me say that? What would I mean by that? Okay, wait. Wait. Sorry. He says to himself now, if I was standing behind someone, what would make me say that? What would I mean by it? The reader is advised that he can only arrive at the deep structure of this book, and through the deep structure arrive at the semantics, if he attempts to generate the book for himself. Okay, so we have to okay, and the author's wishing us luck. All right, cheers, author. Okay, so that's the structure. It's divided into chapters, and each letter has a 6 tuple of natural numbers associated to it. All right, okay. Okay. Now let's see how to read this book. So how should we read this? Reading books is an art to which many pretend, to which some aspire, and to which few attain. Okay, that I can kind of agree with, I think. I feel like reading a maths book is different to reading like a fiction book. Like, you have to approach it differently. Let's see what he has to say. Nothing outside the realm of mathematics is more beautiful to behold than a beautifully read book. Okay. The art of reading books beautifully cannot be imparted in a few lessons. It is difficult to give hints without incurring the dangers of becoming fatally lucid. Okay. Okay, so he's hoping to give us some advice. Here, as in so many things, it is really the man who is totally at sea, who has got both feet firmly on the ground. Okay. Okay. It is the author's general impression that, at first reading at least, it is unwise to read the book on too many levels at once. For most readers, it will in any case be impossible to penetrate beyond the lowest level or two. Okay. Okay. These should be okay. Okay, and now he's just talking about categories. Okay, so he's saying, it's beautiful to read a maths book well. It's an art. You know, you have to train it. You should read the levels on. You should read the book on different levels. You know, general advice. And now he's just talking about categories. All right, cool. Consider a category in which there is at most one arrow between two objects. Okay. And in which every isomorphism is an identity. Okay, so there's no like isomorphisms between different objects, I guess. We only have the identity. Products and co-products exist. Okay. Moreover, product distributes over co-product in the sense that the dotted arrow exists. All right, let's break this down. Let's break this diagram. This is the intro, by the way. This is him telling us how to read the book. This isn't even like. Let's have a look. Let's break this down. Okay, let's have a look. What's going on here? Okay, so we have products and co-products exist, and product distributes. So this product here distributes over the co-product. Okay, so he's so this is like the categorical version of saying that, like, if we do the product of A with the co-product of B and C, like somehow we can distribute this in, but it's not like identically equal. It just means that, like, you can have this dotted arrow in this diagram. Okay. I mean, sure. Okay, okay. Interesting. And I guess all of these arrows come from, like, the definition of a product / co-product. Like, all of these are like projections or something. Okay, fine. So we're just considering this category then. I'm not exactly sure why, but we're considering a category now. Let's see where he lands with this. Further, assume the initial and final objects 0 and 1. So we have initial and final objects. And a contravariant functor from the category to itself that is alternating on objects. And preserves no arrow except 0 to 1. Okay, this is confusing me. It's alternating on objects. Then it is possible to think, because this category is okay. So he's given us, so apparently a category in which, oh no, did I close Epic Pen? Whoopsie daisy. Oh, sorry. What did I mean to do? Oh, no, delete. Yeah, like that. Okay. Apparently, a category in which you have products. I'll explain what a product and co-product is in a second, don't worry. And co-products, we have 0 and 1, and there's like this like contravariant functor property, let's just say it like that. Then this is a Boolean algebra. Okay, I'll have to think about that after the stream. What is a product / a co-product? Well, we can think about set theory, right? I feel like that's probably the best way to get intuition about this. So if we think about sets, right? Consider the product. So say we have two sets A and B. Consider the product A cross B, right? This gives us like two sets. Sorry, this gives us a pair AB, right? Now, categorically speaking, what's going on here is we have a map, right? We have two maps actually, from A cross B into A and from A cross B into B, right? And what do these do? They just map AB to A and AB to B, right? So in other words, if we put like A cross B here, right? We can map both out into A and into B, like so. And there's some oh dear, oh dear. There's a uniqueness. There's like a oh dear. We have this like oh no. Wait, what's the diagram again? I've forgotten what the diagram is that expresses this. Hold on. Let's take a look at the actual diagram. I'll notate on the wiki. I've forgotten the diagram. But basically like it's like the categorical version. The products are like the categorical version of like Cartesian product, and coproduct is like the categorical version of a disjoint union. So let's have a look at the exact definition because I've forgotten it now. Oh yeah, here it is. Here it is. Okay. Oh yeah. Okay. Yeah, I remember now. Okay. Yes. So if we have two objects A and B, right? If you have two functions which go from say like x to A and g which go from x to B, then we have this happening here. So we have two functions f and g. We also have our product A cross B associated, which has two different projections. And the definition of a coproduct is that there exists a unique map which goes from X to A cross B, right? So we're given, which makes this whole diagram commute. So basically what that means is if you did, let's call this function, I don't know, H. If you did H, if you did pi A of H of X, that's the same thing as doing F of X, right? And remember, pi A just picks out the A coordinate. So really what H is equal to FG, right? So it does F to the A to, it does F of X, G of X, basically, right? So in the sets example, but in general, in category theory, it's just, it just exists and is unique, right? And this is like how they generalize the notion of like products and co-products, of products in set theory. And basically with co-products, you just like reverse all of the arrows, essentially is what you do. So, you know, the fact this doesn't always have to exist in a category. I can't immediately think of a category which doesn't have products, but this doesn't always have to exist. So that's what he means when he says that products and co-products exist. He means that like for any objects A and B in the category, you can always form this coproduct. Like this map H will always exist, basically. So yeah. Now, how that gives you a Boolean algebra, I am actually not sure. I would have to I'd have to spend quite a long time sitting down with like all of the definitions and trying to unpack them. But apparently, if you have products and co-products, and they commute in this crazy diagram, and final and initial objects just mean that there's like exactly one map going into the final object, and there's exactly for every. Okay, sorry, I'll write that down. So for all x in the objects, there exists one map from x to 1. That's the final object, and there exists one map from 0 to x as well. So that's just what final and initial objects are. So if we have those, which I assume are like true and false in this case, but I don't know, and a contravariant functor from the category to itself. So that's just like a function which maps objects to objects and morphisms to morphisms in like a nice way, basically. Then it is possible to think, because the category is a Boolean algebra. So apparently this is like the category theory version of a Boolean algebra, which again, I'll have to look into. But basically, this is him making even the introduction is being made complicated. Like he can't just say things are true and false, he has to say this. I guess it's on brand for the book. But yes, okay. Certain obvious refinements will bring the reader face to face with logic. A little logic of this naive sort may occasionally be found helpful in reading the book. Okay. It is finally suggested that the reader begin reading at some definite point, say the first chapter. Okay, that we can do. We can start at the first chapter. that I understand. That's fine. We can start at the first chapter. Okay. All right, before we actually start on the first, sorry. What is everyone's thoughts on that introduction? Has that whet your appetite to like dig into this book? Personally, my thoughts are, this book sounds quite fun. The author sounds really clever. I feel like the guy who wrote this is like a genius or something. And I feel like there's going to be lots of hidden references that like, if you're like better at maths, or like maybe he's like even interweaving like different like literature references that I'm not getting, but I feel like there's going to be so many references in this book that that like so many little Easter eggs that he's put in there that maybe we'll catch some of them, maybe we'll miss some of them. But yeah, this guy sounds like whoever made this book, Carl Linderholm, he sounds he sounds like a clever cookie. Very interesting. Sounds like a fun book to read and also funny. Yeah, agreed. A proset is a category with a unique morphism from x to y whenever x is less than or equal to y. Okay. Oh, so is that like the category version of like a partially ordered set or something? Okay. Interesting. So I assume this was a proset with extra. Oh yeah, pre-ordered, yeah. This was like a proset but with extra stuff attached as well. Okay. All right. Okay. Cool. Okay. All right. Now we're going to dig into the meat of the book. So we're starting with arithmetic, and the first question is whether anybody really counts. Okay. First objection. In order to really count, the counter must know the names of numbers. But no one knows the true names of numbers because Englishmen call them one thing, Chinamen another, so no one really counts. Okay, that's an interesting like philosophical point. It's like, because you call them different names, they're different things. And so nobody's doing the real true counting because you're using different names, so nobody's like talking about the same thing. Like the English are counting in one way, the Chinese are counting a different way, or whatever. Now, this is definitely feels false. This statement feels clearly false. But I guess philosophically it's like interesting to like ponder, like why exactly is this false? So I guess we're going to see the reply. It isn't really category theory. Alternative. Yeah. No. Yeah, that. You know, I agree with that. Yeah. It's like yeah. Okay. All right. What's the objection? You don't have to know the real names of numbers in order to count. Okay. You can call the numbers anything you like. And you need not use what are usually called numbers at all in counting. Interesting. Or to put it otherwise, almost anything can serve as a number if you so desire. Simply transfer the structure of the counting system to another by means of a bijection. Mathematicians never claim to know about the elements of a system, only about relations between them and structures imposed on them. Okay. Interesting. So that's a good point actually. Like the literal symbol, like the literal symbol 2, I guess isn't actually the number 2. It's just like what we've denoted it as, but like the set of natural numbers, or like the set of symbols of natural numbers, like 1, 2, 3, is like in bijection with like the actual natural numbers in a sense, I guess. Interesting. This is like quite a philosophical point, I feel like. Mathematicians never claim to know about the elements of a system. So like we don't know about the like symbol 2, I guess. Just like how the symbol 2 relates to like the symbol 3, like we know, and 5, like we know 2 plus 3 equals 5, say, but like we don't know anything about this like actual symbol. We just know that like this relation holds, and so on and so forth, I guess. And we're like in bijection with whatever the true numbers are. But like this isn't actually a number. This is just like this is just the pre-image of a number under like a bijection, I guess. Interesting. So you're saying the way we use numbers makes them numbers, not how they're written. I think so, yeah. I think that's his, because the objection was you say 1 in one way and this guy says 1 in a different way. Like the Serbians say jedan and the English people say 1, so now they're different. And his reply to that is it's not the way we say or the way we write numbers that make them numbers. It's actually just how they relate to it. It's just the relations between the numbers that matter, I guess. And he's using the formal mathematical terminology of like a bijection, which just means like a one-to-one map. I guess between the symbols that we use and the real things. I suppose that's what he's saying. So that's his reply to that objection. But then there's another objection. Furthermore, although in a certain language a man might be said to count as far as a certain number, after that he must stop. Okay, so this sounds like a finitist argument or something like that. For instance, in English, no one can count higher than 999,000. Okay, blah blah blah. Okay, 999,000. Whatever this massive number is. 900 blah blah blah. In Melanesian pidgin English, many speakers cannot count higher than one fellow man. That's kind of funny. But in counting, if the counter stops at a certain point, he is not really said to count. Okay, so basically now he's saying, yeah, I guess this is like, I don't know actually that much about the philosophy of like constructive mathematics, to be honest, but I guess this is like a constructive argument. I don't know. You'll have to let me know actually. This sounds very sort of finite, finitist, like, well, you can only count so high. So like once you stop, like anything above that, you like can't count that, I guess. Something along those lines. Like infinity doesn't exist, basically. But I guess my objection to that would be like, okay, well, what is the biggest number? Because I can always just add one, right? I don't know. Let's see what his objection, what his reply is. Well, I guess also this guy is using the same argument as before, just in a different form. Instead of saying you say the same number differently, now he's saying you can't even say that number. You don't have the vocabulary for that number. But I guess I could just say the same thing. It's like I don't need a name for it because like it exists. I can add it. I can add it. You know, I can do arithmetic with it. I don't need a name for it. Let's see what the reply is. I'm sure there'll be a clever reply here. It's true that most languages only have a few names for numbers. Okay. Whether there are any exceptions to this rule is a question I leave to linguists. The remark about Melanesian pidgin may be misleading, since one fellow man means 20, just as two fellow hand, one fellow foot means 15. Okay. Um, as far as it concerns the English and most civilized counting systems, the objection is a valid one. Okay. The trouble is that the rule for naming the successor of a number after you have named the number is not everywhere defined. There is no successor function. Thus, the English system is mathematically backward, compared with certain primitive systems. This is the reason why children ask what is the greatest number, but it does not prove that no one can count. It proves only that aged, civilized non-mathematicians do not count. This we knew already. Do you like the definition of a group as a one-object category? I do like the definition of a group as a, well, I guess it's a one-object groupoid, right? But I do like that definition. The highest number in Japanese is Muryo Taisu, which means 10 to the 68. Wow. Okay, yeah, that's crazy. Okay. The largest number is the largest number you can create using set theory. What's that? That's like some like crazy cardinal though, no? I guess that's not a natural number though, right? I don't know. Mm. Okay. But what he's saying here, right, slightly confuses me. Because what's he saying here? He's saying it doesn't prove that no one can count. It only proves that aged, civilized, non-mathematicians do not count. So, is he saying most people don't actually count? The objection is a valid one, he says. He's saying the rule for naming the successor of a number is not everywhere defined. Maybe he's saying just like in English you can't count in English, but you can count, but it's still possible to count. You just need a well-defined way of naming the successor for every single number. Whereas once we get high enough in our language, we don't have a name for the next number, so it's not everywhere defined. I suppose that's what he's saying. So you can't count in English because our language system doesn't allow us to count past whatever the biggest number is. But even then I would disagree, right? Like, can't I just start saying 10 to the whatever plus 1 or whatever, or like just saying it in standard form instead? I don't know. Maybe that's not allowed for some reason, but I don't know. Like, why can't I just say 1 times 10 to the, and then whatever? And once my exponent of 10 becomes big enough, can't I just, like say 1 times 10 to the thing, and just keep doing that forever? I don't know. Maybe he thought maybe, I don't know, maybe that's just not allowed. Hello, K-Star, hello. Do you have an exam today? Or are you done? I don't know. Okay, the final, oh no, maybe not the final. Another objection. If anybody could count, then certainly mathematicians would be able to count. But mathematicians pretend to count by means of a system supposed to satisfy the so-called Peano axioms. In fact, there cannot be any Peano axioms, since they were really invented by Dedekind. Hence, even mathematicians cannot count. Further Furthermore, the piano only has 88 keys. Hence, anyone counting with these axioms is soon played out. Okay, that's got to be a funny joke, right? This last bit. The piano has 88 keys. Last one today. Good luck. Good luck. We're currently reading a book called Mathematics Made Difficult by Carl E. Linderholm. And we're currently we're talking about, can we count? Can we actually count? Let's have a look. So he's saying mathematicians pretend to count by means of a system supposed to satisfy Peano axioms. But there can't be any Peano axioms since they were invented by Dedekind. So I feel like this is more of a joking objection, right? This is more of like a linguistic joke, I feel like. Let's have a look at the objection, though. I don't know. Reply. Dedekind's version is indeed equivalent to Peano's. Okay, I didn't actually know this, by the way. I didn't know that Dedekind invented the Peano axioms before Peano, but okay. Although it was stated differently. Dedekind's paper is still of great historical interest. Maybe one day we should read this paper. But okay. And contains many suggestive ideas. But Peano, G for Giuseppe, was an influential innovator in ideas and in the mathematical notation of the century, and he deserves the renown for his beautifully stated axioms. He invented a system of stenographic shorthand, but I am unaware of any musical works. Okay. I feel like this is a reply to the joke about the 88 keys, because he's saying a piano only has 88 keys. So if you use the Peano axioms, you can't go above that. Okay, so this is the number 89 apparently. So exposed, roasted, objection, destroyed. Okay. Okay, this guy keeps on objecting. He's got more. Furthermore, Peano's axioms imply a supposed well-ordering, whereby there is a least number with a given property, provided any number possesses that property. Okay. So he's saying the well-ordering principle holds, but the least number cannot be named in fewer than 21 English syllables. Oh, sorry. The least number that cannot be named in fewer than 21 English syllables has just been named in fewer than 21. Yo, wait, this one is kind of a wait. This is a creative one. The least number that cannot be named in fewer than 21 English syllables. The least number that cannot be named in fewer than 21 English syllables. Sorry, I probably over-counted there, but whatever. Has just been named, I assume that was 20 syllables, has just been named in fewer than 21 English syllables. Wait, that's actually creative. I didn't think of that. Okay, that's creative. Hence, no number exists. So this is an objection to the well-ordering principle that cannot be named in fewer than 21 English syllables. But there are at most 10,000 such syllables, hence at most 21 to the 10,000 numbers. But then mathematicians cannot count to 21 to the 10,000 plus 1. Okay, hold on, this last bit went over my head. No number exists that cannot be named in... Wait. No number that cannot be named in fewer than 21 English syllables. But there are at most 10,000 such syllables? Okay, now I'm confused. What does he mean there are at most 10,000 such syllables? No number exists that cannot be named in fewer than 21 English syllables. This very last bit is confusing me. Oh, and of course, the reply is an exercise. The one reply that the one objection that I don't fully understand, the reply is an exercise. Isn't that just perfect? This logical paradox is called the Richard paradox. I don't know whether that guy's French or English. It is a question of foundations of mathematics rather than mathematics itself. At least I hope so. The reply is left to the reader as an exercise. Okay, so we have to reply to this, but I don't fully understand the very last bit of what he said there. That's why I can't really reply. I guess the first bit, with the well-ordering principle, the least number that cannot be named in fewer than 21 English syllables. Oh yeah, because I guess if you have that least number, which is named in 21 English syllables, but then you can name it as the least number, but then there's another one, but then it's in the set, so it's like a contradiction. So what's going on there? I guess that set is just not well defined or something. Like this, some like Russell's paradox or something. This is a book by Carl E. Linderholm, called Mathematics Made Difficult. Okay, I'm gonna look up the Richard. Don't tell me you're gonna leave Carl E. Lind. Okay, I'm gonna look up the Richard paradox because I want to see what's going on here. Let's take a detour into the Richard paradox. Motivate carefully between mathematics and meta-mathematics. I've never actually heard of meta-mathematics before. That's interesting. I've never heard of meta-mathematics. Hello, Oleosaurus. Welcome back. The paradox begins with the observation. For example, the real number, the integer part of 17. Okay. The capital of England does not, nor the phrase, the smallest positive integer definable in under 60. Okay, is this Berry's paradox now? I feel like we've gone into Berry's paradox rather than Richard's paradox. Russell called Berry the only person in Oxford who understood mathematical logic. That's funny. Oh, I see. This one was also okay. This is probably the one that he's talking about. Okay, let's have a look. Let's have a look at this explanation. I feel like this might be slightly more clear. Since there are only 26 letters, okay. There are finitely many phrases of under 60 letters, and hence finitely many positive integers that are defined by phrases of under 60 letters. Okay. Since there are infinitely many positive integers, this means that there are positive integers that cannot be defined by phrases of under 60 letters. Okay, I'm with you there. If there are positive integers that satisfy a given property, then there is a smallest positive integer, yep, well-ordering principle, Therefore, there is yep, okay. This is the integer to which but the above expression is only 50. Yep, okay. I'm with you there. I'm with you. I understand this. I understand this paradox. Okay, this so far is what I understand. Okay. But it's a rather berries. Okay, let's have a look. What's the resolution then? In the word definable. Not name. The term nameable is also one that has ambiguity. Okay. Interesting. Hmm. So so I understand the paradox, but I don't understand the very last bit that Linderholm is talking about here, where he says, "No number exists that cannot be named in fewer than 20." Sorry, there are at most 10,000 such syllables, and hence. Oh, is he saying basically there's only finitely many numbers that could have less than 10,000 syllables? So then, oh, I see. Okay, I don't know where this 10,000 syllables came from, but let's assume that there are 10,000 syllables. So he's saying the amount of numbers that can be defined in under 21 syllables is 21 to the 10,000. But then you can't count past 21 to the 10,000 plus 1. Yeah, okay, fine. Yeah, it's an upper bound. Yeah, okay, let's say that. Then you can't count to the 21 to the 10,000 plus 1 because there are no numbers which can be defined, which are in the set of things that can be defined in less than 21 syllables because of this paradox. I think that's what he's saying. That's what this last part is saying. Okay, fine. Okay. So I guess okay, what's the response to that then? I guess yeah, what do you mean by like defined? Or like what do you mean by yeah, I guess what do you mean by I mean it's still like you're still talking about like the English language, like the names of the numbers rather than the numbers themselves. I guess that's where the issue lies. I guess that's my response to the to the exercise. Um, what was? Let's have a look. Uh, the term nameable has this systematic ambiguity. Yeah, so it's just ambiguous, right? Okay, okay. Yeah. Okay, okay. Fine. So that's an intro. I've never heard of that. That seems like a legit thing. Berry's paradox. Okay. But okay. What's the fifth objection? Only mathematicians really count, but they are disembodied minds. Hence, a mathematician is not anybody. Okay. Okay. Reply. So then, how did I write this book? Okay. That was pretty cold. That was tough. That was epic. That's tough. Okay. Really, to count is to count realiter. That is by means of things. Rebus. Okay. But only children enjoy rebuses, and children do not count in a serious argument. Moreover, counting by means of things usually means counting fingers, which are not bodies but parts of a body. Those who count on their fingers admit they cannot count well. Um, Okay, wait, hold on a minute. Really, to count is to count by means of things. So you're either counting on your fingers, 1, 2, 3, 4, 5, or you're counting like the number of like, I don't know, water bottles on my desk or something. Um, and then he's saying only children enjoy rebuses and children do not count in this. Okay, I mean, this is like ridiculous. Okay. And the reply is, on the contrary, counting on the fingers is excellent exercise in finite cardinal arithmetic. Okay, this subject is treated in a later section. Okay, all right. So more to come on counting on your fingers, I guess. At present, we are concerned with counting per se. Okay, so he's saying, so this is like how he hooks us in, you know? Okay, there's more objections. This is amazing. Mathematicians assert that the set of numbers is a non-empty infinite set, but that which is infinite has no parts, since a part is divided from the whole by a boundary. Uh, but only the empty set has no proper subsets, i.e. no parts, hence there are no numbers. Um, okay. This is, again, a weird objection. I'm curious what the reply is going to be. A set is infinite in mathematics not if it is infinite unconditionally, but if the set of cardinal numbers of finite subsets is unbounded as a set of natural numbers. This is obvious for the set of natural numbers itself, since the cardinal number of that is n. Oh wait, hold on. Okay. According to another definition, a set is infinite if the set of natural numbers can be injected into it. Okay. Okay. The identity function is such an injection for the set of natural numbers. Another possible definition requires a proper injection, and so you just do n plus 1. Okay, so this guy's saying, I don't really understand the objection. He's saying infinite sets have no proper subsets or something like that. And so because you say that there are infinitely many numbers, really, actually every infinite set is just the empty set, so there are no numbers. But he's saying that's not, you've got the wrong definition of infinite. So one definition is if the set of cardinal numbers of finite subsets is unbounded. Okay, so in this case, the cardinal number of this finite subset is n, and n is obviously unbounded as n goes to infinity. Or if the natural numbers can be injected into a set, then it's infinite. And that again is obvious for the natural numbers. And you can also get a proper injection by adding 1. Okay, fine, okay. Okay, we just have an introduction to Peano's axioms now. Cool. Okay, so that seems to be like the first batch of objections. So we have successfully defended counting. Okay, so this guy threw everything he could at counting. I mean, there was some interesting philosophical questions though. I think the most interesting objection that was mentioned there was probably Richard's paradox or Berry's paradox, where he said like it was the one about the syllables, like you can't define it on under 20 syllables or whatever, like something along those lines. That was actually interesting. That was a good objection. Some of them were like funny, like the piano one, like how can you use Peano's axioms when there's only 88 keys on a piano? And then he responded by writing 89 as 0 plus 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 plus. Okay, that was kind of funny. But okay, so we've defended counting. So we've established that we can count. And now we're moving on to Peano's axioms, apparently. Okay, let's have a look. N0 is a set, 0 is an N0, plus a function. If E is in zero, sorry, if zero is in E, which is a subset of n0, and if I guess like the successor of if you take the successor of everybody in E, you're still a subset of E, then E is the next. So this is like induction, basically, I think. Oh yeah, 3 is the induction axiom, yeah, so this is just induction. Plus is injective, yep, okay. Plus is the successor function, I think, by the way. Yeah, he just doesn't write suck. I guess this was like the notation in 1972. And 0 is not the successor of anybody. So 0, 1, and 2 basically tell us that we can count, right? Because we have the number 0. Firstly, we have a set. Then we have the number 0 to start out with, and then we can add 1, so we can just count. So we can count based on axioms 0, 1, and 2. So what's the point of the rest of the axioms? Well, axiom 4 tells us that the successor function is injective. So we don't want the successor of 1 to be equal to the successor of 2, right? When we take the successor of 2, we want to get another number. So we need it to be injective, basically. The Chinese system of naming years is isomorphic to this sequence, apparently. I did not know that. If anyone here is Chinese, you can confirm or deny. Is inductive and injective, but fails 5. Right, because 0 is... Right. This is injective, and it's inductive, but because 59 looped background, we don't get an infinite set. So we need to just keep going. We can't ever loop back round to 0. So that's why axiom 5 is there. Non-inductive systems like this. Okay. Away, with, rum, by, gum, with. Okay. Okay. Never say die. I give up. Okay, I think this is inductive. I can't actually tell why this is not inductive, like right off the bat, to be honest. Oh right, I guess because you could take the set never say die. Oh no. You could take the set I give up, and you could take like the successors of everybody in here, and you would still be a subset of I give up, but you would not be the whole counting system because there's these guys which are completely separate from these guys. So you need induction so that there's not like two different counting systems going on here. I think that's what it is. Hello Neox Schnish. We're reading Mathematics Made Difficult by Carl E. Linderholm. Yeah. Why is 0 in the natural numbers? I mean, he is writing n0 to be fair, so that kind of implies that n on its own does not include 0, if that makes you feel happy. Sitzwit says, what's your major? I do maths. I study maths at Cambridge. I answered that some people really count, namely mathematicians, some savages, and some 2-year-olds. Anyone who counts possesses a counting system. Okay. Mathematicians have a universal counting system n0 called the natural numbers. Never mind. He is including 0 in the natural numbers. But he who counts both universally and naturally counts really. Okay. Interesting. Some 2-year-olds count as follows. 1, 2, 3, 3, 3. Okay. But this implies the existence of this counting system. where you start at 1 and you go to 2 and then you go to 3 and then you loop then you just start at 3 3 3 3 3. Um, but since if S is defined by 1 maps to 2, 2 and 3 maps to 3, then S is a function. Oh, wait a second. This is a counting system? Interesting. Okay. That's interesting. Okay. So you can construct like a counting system out of like these 2-year-olds counting systems. Interesting. Okay. Moreover, many of these so-called primitive languages have such a system. Okay. Okay. So what's the question, right? So this was like his final conclusion to the counting saga. He tells us about the piano axioms, um, and he says, okay, here we go. All right, let's move on to the second question. Whether it is natural to use the natural numbers. Okay. Um, isn't I'm Ushnish from India. Okay, nice to meet you. Like, isn't mathematics already difficult enough? Well, we read the introduction in which he said, um, the real enlightened people um, think that 17 times 17 is really complicated, and the fact that in a principal ideal, um, the thing like generated, if E is a subset of it, then the ideal generated by E can also be generated by a subset of E is not complicated. That's what he said. So we're trying to gain enlightenment here, mathematical enlightenment. Okay, what's the first objection? They would seem to be very unnatural, since they involve sets and functions. These are abstractions and innovations, probably irreligious, impractical, and disrespectful to the flag. In Britain, the Queen. Okay. Okay. Oh, this is funny. Okay. All right. So I guess to me, this is. I guess to me, it says um, it's an objection. It's offensive to the king. What's the reply to this? How do you stop someone from spouting propaganda? Sets and functions are more natural than arrangements of n. Are more natural than arrangements of n-like objects in a line without repetition. Um, independent variables, and such paraphernalia, all of which belong in the Natural History Museum because they used to be natural, but now they are history. These relics are equally abstractions. Mathematics is not meant to be practical. Sets and functions are intensely pious and loyal. Okay, this is low-key like a this is kind of a schizo like reply to the objection. Sets and functions are intensely pious and loyal. What do you what do you mean by that? What? Okay. Um but okay, sure. I guess he's saying like if you have stuff in the Natural History Museum, they used to be natural, but now they're history, so they're equally abstractions. Okay, I mean this whole like objection and the reply is crazy to me. Okay, we're just gonna move past that. Um, what is natural can be easily understood by children, but only a genius can make sense of all this stuff. Uh, Children aged 12 to 18 can easily learn the Schroeder-Bernstein theorem and the proof that finite fields have prime power order. That's funny. Okay, let's have a look. What is the Schroeder-Bernstein theorem? Oh, I did know this. This was like the very, very, very last part of numbers and sets. The proof of this is low-key like complicated. This is funny, yeah. Yeah, someone's got to get Dennis in the chat. Someone has actually got to get Dennis. This is more like a English and history class. I feel like it's more of like a it's more of like a philosophy type thing. Yeah, I just don't recognize the name. Okay, guys, I know the theorem. Okay, apologies. I don't have exams anymore, so it's fine. All right, let's have a look. What? Okay, cool. Um, so he's just claimed that the children can learn the Schroeder-Bernstein theorem and the proof that finite fields of prime power order. Sure. Okay. Okay. Sure. If you say so. The piano axioms are already 70 years old, but is it unnatural in science to hang on to what is passé or old hat? At present, the axiom. Okay, they're still useful basically. So then they're okay. Cool. The piano axioms describe the natural numbers internally rather than as a universal object in the category of pointed functions. This is good. This would seem unnatural since categories are the mathematics of the future. This is this is a based objection. I'll give this a brilliant. This is a based objection. Um, rather than as a universal object in the category of pointed functions. um, yeah, but no, why would you not define them as a universal object in the category of pointed functions, since categories are the mathematics of the future? And he even concedes this is partly true. The future will tell. Okay. And this was written in 1972, by the way. So this guy called it. Um, okay. The additive group of integers is basic, and that includes the natural numbers as well as the negative numbers. Why not start with that group and kill two birds with one stone? Okay, again, this was Loki. He Loki conceded this point. He just said, "You do it your way, and I'll do it my way." So he's basically saying, "You know what, Fairs? Like that's a fair objection." Yeah, okay. So, I guess this one is kind of reasonable. It's like, why not just start with the integers? I guess natural numbers are, in a sense, more natural. But I don't know. He basically is saying, like, whatever, if you want. Everybody does arithmetic in decimal or Arabic numerals. This seems like a good system and doesn't require all this abstraction. You're making mathematics too difficult. First of all, there are no Arabic numerals since they were invented by the Hindus. Okay, okay. Um, some shade. Apologies to my Arabic audience. Some shade being thrown on you guys. The Hindus were the ones who invented Arabic numerals, apparently. I can neither confirm nor deny this. Secondly, they involve the arbitrary choice of 10 as base. Mathematics requires considering numbers in infinite sets, as well as one at a time, and for this purpose, numerals are insufficient. A numeral is a sequence of digits. What does this mean if n0 is not already available? That's a pretty decent objection, no? Sorry, a pretty decent reply. He's saying like, what even are the numbers that you're using? Like, if you don't know like this, if you don't know n0, like how can you even define this function? What is 9? Let's have a look. Also, what is a pointed function? I did see that question. I will answer in a second. Let's have a look. Where's this? Oh no. Oh no. These are the exercises. Oh no. Maybe it's lagging. Oh no. Sorry. Never mind. Where's his Oh yeah. Here we go. We can do the exercises later, I guess. Uh, a short account of the history of mathematics. Okay. What is a pointed function? I think, I mean, my understanding when I see the word pointed function is I think of like a space with like a base point, and I just think of functions that preserve the base point. But maybe I haven't actually, like, maybe I'm thinking of the wrong thing. Because like those are also called based functions, so maybe a pointed one is different. Let me have a look. Yeah. It just yeah. Okay, yeah. It's just a function that preserves base points. Okay. Before you study numbers, you should read Genesis, Exodus, and Leviticus. I wonder if 10 is just the reference 10 is just the Bible, or the Old Testament or something. Reply to objection 7. I did. Look now toward heaven and tell the stars if thou be able to number them. Since the number of stars is not known, and the naked eye not mentioned, it is natural to establish n0 before beginning the project. That is that's a deep reply, actually. Look now toward heaven and tell the stars if thou be able to number them. That's a that's a good reply. I think that's a good reply. I like that. Is not known and the naked eye not mentioned, it is natural to establish n0 before beginning the project. That's that's a good reply. I like that. Okay. Peano's axioms are clearly nonsense. Let F be a bijection from the supposed n0 to a set of filing cabinets. Lock F of 0, put the key in F of 1, lock F of 1 and put the key in F of 2, and continue by induction. Now all the cabinets are locked, with their keys locked inside their neighbors. That is obviously impossible, hence n0 does not exist. Reply. Filing cabinets are not mathematics. Okay. I like how this guy spent so long on objection 8 and he just shut it down in one sentence. But we got more on induction. Induction is nonsense, since it purports to prove that all girls are blondes as follows. It is sufficient to show that if one of any n girls is a blonde, then they are all blondes. This is clear if n equals 1. With n greater than or equal to 1, suppose the proposition is true for n. Then it is also true for n plus 1. Suppose one of n plus 1 girls is a blonde. She is either among the first n of the girls or among the last n. Say the first n. These, by the hypothesis n, are all blondes. Then at least one of the last n is a blonde, and they two are all blondes. Now all the n plus 1 girls are blondes. Okay, what's the reply? This is ineptly stated, since the same thing can be proven more easily with hydrogen peroxide. Also, it does not work if n plus 1 equals 2. Okay, wait, hold on a minute. Oh, interesting. It doesn't work if n plus 1 equals 2. Wait, what if I just... Oh, but it doesn't hold for n equals... Wait a second. It's sufficient to show that if one of any n girls is a blonde, then they're all blondes. Wait, so if we have two girls... If we have two girls, and... Oh yeah, it doesn't hold. Yeah, we can't imply this. Yeah, yeah, because it doesn't... Yeah, because the... Okay, fine. It just doesn't hold. Okay. The natural numbers bore me to tears. But it would seem unnatural to use anything uninteresting in mathematics, since this subject is intensely interesting through and through. Okay. Reply. All numbers are interesting, since the first uninteresting number would be interesting. Oh yeah, that that's a great objection. The first uninteresting number would be interesting because it's the first uninteresting. Bro, this guy is too cold. Or better, no number is interesting because the system of all natural numbers is very interesting. Okay. Okay, these objections were quite weak. These objections were quite weak, I think. I think he put them down pretty easily in this section. And now here we have his final thoughts. I answer that it is very natural for mathematicians to use natural numbers, since without them they could not do mathematics. The natural number system is a universal pointed function, and so must be natural, since universal objects are a natural idea. Okay, now he's getting into category theory. Okay, interesting. Let's have a look. Let's get down to business here. What's he saying? If this sequence, abbreviated X, and this sequence, abbreviated, probably abbreviated Y, are pointed functions. Alright, so we got X is the base point, I imagine. And S is a pointed function from X to X, I guess. A morphism from X to Y is a function such that the squares of this thing, so this square, commute. So that means that Ft is equal to SF. Fs is equal to Tf. Okay, fine. Oh, so this has to be so F has to be pointed, right? Because you have to have like F of X equal to Y, right? By the commutativity of this square. Because this just maps X to Y, and this is an inclusion, so it gets sent to Y. Whereas this just maps X to X, and this maps to F of X. So F of X has to be equal to Y. So F has to be a pointed function, basically. If X has the property that from X to any system Y, there is exactly one morphism, then X is universally repelling, and mathematicians universally find X attractive. Okay. So he's saying that from X to any system Y, there's only one morphism. So there's only one. Okay, so no matter which Y we pick, there's only one function F which satisfies this thing. I think that's what he's saying. Axiom: there exists a universally repelling pointed function. Interesting. So he's saying that the natural numbers satisfy this property. And this is just an axiom. This isn't even a theorem, this is just an axiom. I'm curious what this, I'm going to duplicate my tab with the bibliography so that I can refer to it. I'm curious what his, what he's using here. Oh, number 10 was the Torah, so yeah, I guess basically was just the Bible. Yeah. 12. The category of categories as a foundation for mathematics. Okay, this could be a really fascinating paper to read. I'm gonna keep that open. This could be fascinating to read. Okay, we could read this another time. So we're saying that we can use category theory as like foundations. I did not know that. This could be fascinating. But okay, so his final point is that The natural numbers are very natural to use because they satisfy this like condition, this categorical like universality condition, basically. Um, so n0, the natural numbers are universally repelling, which means that mathematicians will find it universally attractive. I don't know if that's like a more of a linguistic point than anything, but okay. We could read that paper another time because that sounds really fascinating. But let's just press on. I'm just going to take this as a given and not dive too deep into this. But okay, cool. So, what have we established so far? Let's just have a quick recap before we press on. We've established counting is possible. And what else have we established? We've established that it is natural to study n0. That's what we've established so far. And now the next question is, what is 2 plus 2? Okay. I think I'm starting to get what he meant at the start, though. Like, studying this stuff in this much depth sort of gives you like a really it's like really interesting and philosophical in a sense. So okay, fair enough. This is kind of interesting. And then I guess the fact that like that principal ideal fact basically, because like you're basically working off of like the foundations already. So like that fact is not as complicated as the like deeper like axiomatic. Like the closer you get back to the axioms, the more complicated you're getting, rather than like what the ignoramuses, as he would call them, would think, where like the further deep you go into the chain, like the further you press on using the axioms, the more complicated. And it certainly looks that way, and probably in practice, well, in practice it is that way. But he's saying like really, if you really deep it, it's the axioms themselves, and like the closer that you get to the axioms, that's the real like on a philosophical level is more complicated. How do you find out about this book? I don't actually know. I just kind of knew about it for a while, and then I remember Otium sent me a PDF like a few months ago, because I asked him if he had a PDF, but I never actually really read it. But I'm glad that I am reading. This is actually kind of a fun book to read, and it's kind of interesting as well. All right. Anyway, so that's my sort of take on where we're at right now. On to question 3. Whether 2 plus 2 equals 4. Objection 1. When I say to a mathematician, you've come a long way since you learned that 2 plus 2 equals 4, he always makes a wry face. Maybe 2 plus 2 is not 4. Okay. Let's see what his reply is. The comments people make when they find out you're a mathematician are always painful to hear. The average man's notion of what a microbiologist or an anthropologist does is relatively accurate compared with his absurd fancies about mathematical work. Popular notions regarding the spirit of mathematical inquiry are definitely stuck in the Babylonian era. This is especially the case with respect to things like 2 plus 2 equals 4. For this reason, the latter is a principal mathematical shibboleth that others will do well to avoid mentioning in our company. Okay. Okay. So I guess this reply is kind of interesting and kind of true, right? Like if you think about what a biologist does, a microbiologist does, like it would definitely be closer to what the average person would think a mathematician does. Like it would be more accurate. So I guess in that sense, like he's got a point. And then he's put it in his usual charming and amusing way. Hello to Remy710, by the way. Hello. Okay, now the second objection is the following. 2 plus 2 is an obvious fact of everyday life, but everyday life is not mathematics, And hence, in mathematics, it would seem that 2 plus 2 is not 4. Okay. What's his reply to this? If people choose to use addition in everyday life, we do not mind. This makes mathematics neither more nor less valid in its own sphere. So he's saying, what's he saying? Sorry. Hence in mathematics, we'll see. So he's saying like, okay, cool. So 2 plus 2 in everyday life is 4. How does that have any effect on mathematics? Like, it doesn't affect whether or not it's true in mathematics. Like, that's a false implication. That's a fallacy, so to speak. Objection 3. Solomon, a very wise king, says, there be three things which are too wonderful for me, yea, 4 which I know not. Thus, 2 plus 2 would appear to be 3, not 4. Okay, I don't see how that implication even follows from objection 3. And the reply simply just says, he's not writing about mathematics, and he explicitly disclaims mathematical knowledge, for which I know not. So, okay, that was kind of a non-objection, I think. Objection 4. What is 2? Define your terms. Okay, that is a valid objection which has been wrestled with, to be fair, I think. Reply to objection 4. The number 2 will be defined by the above equation 1 plus 1 equals 2. As soon as I get round to defining 1 plus. Okay. Okay. Cool. Okay. So I low-key think the objection 4 got the better of him, unless he defines 1 and plus. But okay, we'll move on. Objection 5. This would seem to imply that 2 games of chess equal a game of bridge. But chess is... Wait, what? What? What do you mean this would imply that 2 games of chess is equal to a game of bridge? I don't understand. How do you even come to that conclusion? But chess is mathematical in nature, whereas bridges are an engineering problem and merely an application of mathematics. We do not yet assert that 2 players... Oh, fine, okay. Right. Because a game of bridge has 4 players. Okay. We do not assert that 2 players plus 2 other players make 4 players. This is adding things, which goes beyond the scope of this section. Okay, now this is low-key a deep philosophical point. This sort of ties back to the very, very first objection, where we were talking about, like, what does the symbol 2 actually mean? Here he's saying the number 2 does not correspond to 2 things. This is, in and of itself, its own thing. So when we say 2 plus 2 equals 4, we literally just mean the number 2 plus, whatever plus means, the number 2 equals 4, like it's related to the number 4 by this relation. We're not saying 2 things plus 2 things is equal to 4 things. That's going beyond the statement 2 plus 2 equals 4. So that's kind of an interesting philosophical point, or at least that's how I interpret his reply to objection 5. Some of these objections are so bizarre. How does bro think up these things? I don't know how he thinks. I mean, you know what? I respect the hell out of it, but I don't know how on earth he's come up with some of this stuff. Okay, fine. But yeah, that's how I interpret his reply to objection 5. Okay, objection 6 says, furthermore, when people put 2 and 2 together, admittedly they usually get 4, but sometimes they get other numbers. So we can't be absolutely sure that 2 plus 2 is equal to 4, but mathematics deals with absolute certainty. Okay, that's kind of interesting. Like, how can you... That's like an epistemological question, right? Like, how can you be sure? I feel like that's more of an attack on the entire of mathematics than specifically the statement 2 plus 2 equals 4. Because he's saying like, well, math says like certainly stuff happens, but he's saying like, well, what if I get a different answer? How do you know that I'm not wrong? You know what I mean? So and I think he's just applying that to 2 plus 2 equals 4, which is kind of, I feel like that's a deeper philosophical objection. But okay, let's see what he says. Our assertion bears no relation to the data of practical experience. Moreover, most people cannot count, let alone add. So he had to take a shot at average people. He loves dissing people. He loves saying like, bro, these guys are idiots. But okay, he's making it very clear that when we say 2 plus, when we're dealing with numbers, we're not dealing with things. We're dealing with sort of more abstract, like these are just like we can say there are two things, but when we say the number 2, we don't mean two things. We just, that is in and of itself is just 2. Like it's its own thing. Like it's not two things, like it is 2. It exists in like some sort of abstract way, I guess, is what he's saying. And he's making this point again and again. Sorry, what was that? Now what was I going to say? Yeah, so he made this point in objection 5, and I think he's making this point again in objection 6. And he had to just put this extra sentence as well. That's funny. Okay. Objection 7. That 2 plus 2 equals 4 is a consequence of the so-called associative law, obeyed by all monoids, including that of the natural numbers. But natural numbers have no organs of communication. Hence, they cannot form associations, groups, or societies. Associativity finished. Associativity is exposed. Don't ever say addition is associative again. It's over. It's over for associativity as we know it. What's the reply? It is the mathematicians who group the numbers, not the numbers themselves. But monoids have the property that makes no difference, that it makes no difference whether we group their elements one way or another, which we call the associative law. Yeah, okay. Yeah, okay. That was an amusing objection. Okay. It would be unnatural to add numbers, since we have already seen that mathematicians make no claim to know what those are in themselves. If you do not know what 2 is, how can you add it to anything? That's an interesting philosophical objection. Because he's been making the point that 2 is in and of itself its own like abstract thing. So then he's saying, well, okay, how on earth can you know what 2 plus 2 is if you don't even really know what 2 itself is? What's he going to say to this? It is true that it is unnatural to add numbers. The natural thing to do is to add or compose functions, and the objector will be relieved to learn that this is what we shall do. So really we're just composing functions, since the functions are induced by the numbers in a natural way that we may speak, par abus de langage, of adding numbers. Right, so we're not actually adding, we're just composing. Is there a difference between counting and adding? I think when you look at the Peano axioms, you can count without adding, because we just define the successor function. Because like we don't define the successor function as +1. It's just like, I think it's like the unique map that makes the Peano axioms work. And then in terms of the successor function, then you can define adding. So I think you can do counting before you do adding, because I don't think you have to define, obviously we know that the successor function is just +1, but I think you can define it as just like the unique map that makes the Peano axioms work. I think. My objection to his last sentence in objection 6 is, let's have a look. What's but so 2 plus 2 is not. How does he know that if a person counts wrongly or not? Yeah, true. Yeah, agreed. All right. What is objection 9? 2 plus 2 can be anything you like, since we may use plus for any law of composition. For instance, if you count, then you'll probably say 2 plus 2 equals 3. And okay, that's true, but like, we're obviously talking about plus. Oh, in his reply? Oh, right. Yeah. I guess that is true. How does he know that it's him that... Yeah, I guess. I don't know. That's a deep, probably epistemological question now. Like, how does he know that he's right or wrong? I don't know. It is true that the symbol plus or any other symbol can be used for any law of composition. Yep. Those who count with 0 would indeed naturally be led to the commutative monoid given by this Cayley table. But this counting system and this monoid can be obtained from n0 by identifying all numbers with each other. Hence, 3 is just another name for 4, as Solomon, of course, realized. Okay, I've never heard this interpretation of that passage, but sure, okay. Okay, cool, okay. I answer, okay, so we've gone through, so, okay, the structure seems to be, he has a question, a bunch of objections, a bunch of replies, and then he gives his final take. So what's his final take? 2 plus 2 equals 4. Mathematicians have established the associative law for the binary opposite operation plus. Okay. But by definition, 2 is equal to 1 plus 1, 3 is equal to 2 plus 1, and 4 is equal to 3 plus 1. Hence, 2 plus 2 equals 2 plus 1 plus 1, which is equal to 2 plus 1 plus 1 by associativity, which is equal to 3 plus 1, which is equal to 4. Now, my objection to this is, how does he know this? Where on earth has he done this? Is this like based on counting? I guess, but how does he know that plus 1 is the successor function? I don't. He just says by definition, but I don't know if this is by definition. Oh no. Okay. I think he's just using plus 1 as a shorthand for the successor of function, for like suc of 2. So like he's saying like 2 plus 2 equals 2 plus suc 1, which is equal to suc of 2 plus 1, which is equal to the suc of 2, which is equal to 4, I guess. I really hope that Solomon is a recurring gag. Yeah, maybe he just will define it later. Yeah, I guess. Yeah, it would be funny if this is like a recurring thing that he does, yeah. Okay, so that was section 1 of chapter 1. Can we really count? So we've got a detailed... We know that we can count. We know that the natural numbers are a natural thing to use. And we know that 2 plus 2 equals 4. That's just section 1 of chapter 1. I think maybe we'll do... Oh, let's see how long this next section is. Oh yeah, I think this is where he talks about 1 and 2. Oh my days, okay. Okay, this is quite... I think we'll go... Okay. I think we'll go until he defines 1 and plus 1. And then we'll stop there, I think. I think that's a decent start. And then we can go again tomorrow or something. All right, let's go back to, okay. Ad astra per aspirin. I don't know what that section what that title means, but okay, let's get into it. Okay. The fact that the reader has been told this does not necessarily mean that he knows what the section is about at all. Okay. Okay. It is the author's fond hope that he may not even know it after he has read the whole section. Okay. Great. Okay, so we're not meant to know what addition is even after reading this section. Though addition in general is a special case of multiplication, here it is thought enough to consider only the addition of numbers, a very special case. Okay. In the dim ages of the half-forgotten past, in Babylon and ancient Egypt, most people seem to have proceeded to learn to do what they thought was adding after having mastered counting. And they then added with the same numbers that they counted with. The childhood of the man is said to mirror the childhood of the race, and among children this traditional course is indeed still followed by many. Should this be so, or ought we rather to add before we can count? We no longer dwell in caves, and the fact that counting has already been mentioned in this book before adding need hardly prejudice the reader to think that it comes first. Interesting. So he's saying, but how can you add before you count? I guess you can. I guess you can. I guess we'll see what his take is. Let's see what he does. Generations have trod, but pity the poor ordinary sod, the present day beneficiary of all their traditional treading. Okay. You have only to pronounce in his hearing the word addition, to conjure up before his fevered imagination a frantic nightmare. He sees the numerals in a black, whose blackness has no bottom to its depth. Okay, we're getting poetic here, apparently. He knows for sure this sum is wrong. This sum right here is wrong. But how? Where? The digits loom larger and nearer. He falls into the blackness. At last, mercifully, he faints. Alas! Yet, in his benighted way, he too has entered ploddingly on the great quest. He is trying unconsciously perhaps, but struggling for all that, to make mathematics difficult. His best effort is a nasty long sum. Very well. Let him whose mathematical erudition is perfect cast the first aspersion. Okay. Okay, this was just poetic, I guess. I like this author. With a little more mathematics, it is easy to produce more difficulty with less effort. Thus, the principle of efficiency is basic, and is discussed further in the appendix. Okay. There is no need to dirty our fingers with sums. They are beneath our dignity. The horrid difficulties of infinite series, or such things as 1 plus a half plus a quarter plus or 0.3333, put these aside. There is a great lot of difficulty to be got out of much, much simpler things. For the simpler the things a man gets difficulty out of, the better his mathmanship. Do you suppose there is much difficulty in such a thing as 12 plus 25 equals 37? Indeed there is. To be honest, the previous discussion of 2 plus 2 equals 4 was mere fool's play. Let us be fair and start with 1 plus 1 equals 2. Okay, here we go. Okay, here we're getting into what is 1 and what is plus. Okay, we're getting into it now. This guy is such a character. I like this author a lot. He's funny. I feel like in real life he'd be a cool guy. And this also links back to what I was saying about the philosophical inversion. Like the further deeper you go, like the more consequences you study of the axioms, the further you're drifting from the philosophical foundations, which are like more complicated in a way. So I guess that's what he's talking about. The trouble starts with that 1. Remember that the experts are less than sanguine about giving real, obvious meaning to such thing as 1. What is the real meaning of 1? Who can say? It is impossible to agree on any meaning, and if the deepest thinkers could agree on some idea of 1, that would be of no real help at all. But let it pass. What can be meant by plus? Principia Mathematica is coming, yeah, is coming. Yeah. I mean, low-key, like, that could be another reading session, perhaps. Since it appears to be difficult beyond all difficulty for the greatest philosopher to say what anything is in itself, mathematicians will customarily come to some sort of agreement about what they will get together and believe about things. Since nobody has the slightest idea, least of all the poor mathematicians themselves, what the things are about which the mathematicians entertain their so-called beliefs, who can blame them for their harmless fancy? Like the world of a science fiction story, a system of beliefs need not be credible. It may be as wild as you like, so long as it is not self-contradictory, and that it should lead to some interesting difficulties, some of which should, in the end, be resolved. Okay, so he's saying we don't actually know what 1 is in and of itself. We don't know what anything is in and of itself. Like, philosophers have pondered this for years, and even they haven't really got a good answer. So what about the lowly mathematician, you know? And so he's saying, fine, we don't actually know what it is. We don't know what 1 really is. But at least what we can do instead is, okay, fine, we don't know what 1 is. But let's just study the relations between 1 and whatever. So we'll take some axioms and we'll just go from there. We'll just take some axioms and we'll go from there. As long as it's not self-contradictory. We can't be self-contradictory. That would be bad. That would be bad. So it is kind of like a sci-fi story, right? Like in sci-fi, we drop into any alternate world we like, you know? And we just go from there. So maths is kind of like sci-fi, I guess, in that way. All right. A plus 0 equals A equals 0 plus A. This is a shorthand way of saying that if you add 0 to any number, whatever, you get the same number. Since nobody knows what a number is, it might begin to appear as if this rule had a very limited applicability. Supposing Mao Zedong to be a number, for example, one could then write the sum Mao Zedong plus 0 equals Mao Zedong. Okay. On the other hand, if he is not a number, it does not say if you can or not. May we put the beloved chairman into our sums or not? Is it a friendly or an unfriendly act? Will he back us up if we do it? Will he turn the cold shoulder and apologize to our head of state for our bad behavior? Is he really a number? Or is it only propaganda? Naturally, the reader shall not find out from me. Partly what is involved here is the belief. Everything, even Chairman Mao, is either a number or not a number. Okay. Okay. He either is a number or not. Okay. Alright, fine. There are a few other little pieces of etiquette, such as never writing plus between any two things except two numbers, and that 0 is a number. The reader had better get used to the idea of not knowing whether Mao is a number. But if he is one, the reader must not write him in any sums. And the author, there's a footnote here, the author is unaware if he has ever written Chairman Mao into a sum. On the other hand, if he is not a number, then I haven't. Okay. The expression believe as distinct from believe is used in this book for something like pretend to believe. See Hippocratic Oath Appendix. Okay. All right. Okay. Um, Part of what has been said is contained in writing that plus is like a binary operation. This also tells you that adding two numbers produces a number. Not, for instance, a suit of cards. Unless the suit of cards is a number. Oh yeah, casually assuming the law of excluded middle. That's a great point, copyright. I know that Dennis or Spectre DNZ would be rolling in his grave right now. Or well, not in his grave, but he'd be rolling right now somewhere. Anyway, yes. So we have assumed the law of excluded middle. For example, if it is the case, as is much rumored of late, that Mao Zedong and Spyro Agnew are numbers, and if it is also the case that Mao Zedong plus Spyro Agnew equals hearts, which heaven forfend, then hearts must be a number. Okay, so this is his amusing way of saying this is a binary operation. Nevertheless, being himself no searcher of hearts, the author does not wish to insist on this conclusion. It is only it is only stated tentatively and subject to several conditions. Okay. Question 4. Whether 1 is a number. Okay, so this was like a little prelude to like addition. It's like basically he's saying we don't know anything. We don't know what a number is. We don't know what adding is. We don't know anything. So we're just gonna instead assume like some axioms and go from there. We're gonna nail down a couple of beliefs that are not contradictory and we're just gonna proceed. And you know, we don't actually know what a number is. So we know that a plus 0 equals a equals 0 plus a. But we don't know what a can or cannot be. Like, a could be Mao Zedong, or it could not be Mao Zedong. We don't know. Like, that is assuming the law of excluded middle. But like, okay, like it could be or it could not be. Like, we don't know. We just have to proceed. This is the background. And now we're asking question 4. Is 1 a number? Objection 1. Numbers are either politicians or suits of cards, but 1 is neither. Therefore, 1 is not a number. Okay. Maybe 1 is also a politician, a young lady, or a suit of cards. I did not say it was not. The set of politicians, young ladies, and suits of cards cannot be properly injected into itself. The set of numbers can. Therefore, some numbers are none of these things. Armies and political parties are given to claiming that numbers are on their side, but they cannot mean all numbers. The allegiance of the divine and mystical one has often been claimed on both sides of a dispute, but proofs are usually lacking. Okay, great, okay. Fair enough. That's a pretty cool reply. Objection 2. Back when you were teaching us how to count, it was made very clear that 1 was a number. There was no doubt about it whatsoever. This would make it seem natural that now, when we are doing addition, it should still be a number. So most likely, you will say that 1 is not a number, just to make us look silly. That's a good objection. This is an objection that I would have in mind, reading this book. Like, you know, you're gonna like bait and switch, you know, you're gonna do something silly. Because like he did say, like he did just move as if it was a number. So what's his reply? This is an example of second guessing. It looks as if I'm about to do one thing, and therefore it is likely that I may do the opposite. The difficulty is that I may go ahead and do the first thing, thus second guessing the second second guesser. So I have, and this is one of the attractive things about mathematics. Sometimes the answers turn out to be just what you thought they would be. Mathematics is a tricky subject. Okay, fair enough. Objection 3. If we say a number of old men were affected with apoplexy and took a number of valerian drops, we always mean several old men and several valerian drops, and never 1. Since a number never means 1, 1 is not a number. Reply to objection 3. The fact that we do not say a number when we mean one is a singularity of usage? That is a tough response. This is like the ultimate like shower conversation. Like when you like come up with the ultimate like clapbacks to to people like dissing you or whatever. This is like, but this book is basically that. That is a good reply. I answer that one is indeed a number. There is no special reason why it is a number because I say so. Now this is basically what he's been building up to saying. He's saying like, I can say one is a number. I've just defined the symbol one such that it is a number. You know, that's just, it is. It just is. Like, I don't know what one is. I'm just saying one is a number. Like, you can't stop me. I'm just saying it is, you know? Now, since one is a number, there is no harm in forming the sum, because remember, plus was just a binary operation anyway. And if we choose to call the resulting number 2, no one can argue. Okay, yeah, that's fair enough. Of course, it is not fair to use the name 2 for the result of this sum if that name already has a number, not another, possibly quite different meaning. Before writing 1 plus 1 equals 2, it is necessary to divest oneself of all preconceptions about 1 and about 2. In other words, it is fair to write it only in case it is meaningless. Goodbye to the idea that 2 is company. Adieu to death and taxes, for they are no longer certain to be two things in life that are certain. We must be ignorant of such fantasies. What is 2 but the other end of an arrow? Okay, well, but what is a number? That is yo crazy-ish. What is a number? That's the question. He's basically saying it's just whatever you like. It can be a number if you want. It just has to satisfy those properties, certain axioms. But like anything you like can be a number. So I'm just saying 1 is a number because I say so. Basically, I have no good reason to say that 1 is a number. But I also have no good reason to say that 1 is not a number. So I'm just going to say 1 is a number and just let it satisfy the axioms and just see what happens. And in the same vein, I could also just call 2 the result of 1 plus 1. And like, I could just say that is 2. However, what if the symbol 2 already has a different meaning? So we need to dig deeper. What is 2 but the other end of an arrow? 1, 1 maps 2. That is tough, to be fair. Okay, so we don't have any preconceptions of what 1 is and what 2 is. We're just going forth. Let's have a look now. Let us be generous with ourselves. Unstinting, profligate, prodigal, let us write 2 plus 1 equals 3, 3 plus 1 equals 4, 4 plus 1 equals 5, and 5 plus 1 equals 6. Unflinching in our audacity, with lunatic abandon, let us dare to inscribe 6 plus 1 equals 7, 7 plus 1 equals 8, 8 plus 1 equals 9. With the famous axiom of associativity, one may then prove 5 plus 4 equals 9 by doing that. What glorious certainty! What a happy ending! Does the reader feel a bit relaxed, cozy, warm, satisfied? A common reaction. It may even be worth the taxpayers' money, paying all those university mathematicians. At least they are busy making sure of the facts of arithmetic. Without them, who knows? Perhaps 5 plus 4 might slip and become 6 instead of 9. It's good to know that things are all right after all. Or are they? Far from it. Mathematical ideas, as they trickle down to the popular mind, become diluted. A sneaking suspicion is abroad that mathematicians, some few evil ones at least, are casting doubt on eternal verities like 5 plus 4 equals 9, or 2 plus 2 equals 4. Fie! There is not a grain of truth in it. The calumny is too low, too base. This vulgar reaction is an excellent case in point for the novice mathsman to sharpen his wits on. Popular imagination conjures up the myth of the wicked professor who teaches that 2 plus 2 is not 4, precisely because it cannot conceive the truth. The truth is much stranger, more monstrous, more impressive. It is not skepticism about 5 plus 4 equals 9 that exists, but skepticism about 5, about 4, and about 9. With a few brackets, it is easy enough to see that 5 plus 4 is 9. What is not easy to see is that 5 plus 4 is not 6. Great delicacy and tact are needed in presenting this idea in conversation, if the aim is, as it should be, to bewilder and frighten the opponent. His level of sophistication is very important. He may know all about it. Then he will utter some crushing reply, like, "So what else is new?" He may even add, "Just finding out about cyclic groups?" Or mention some other concept that you yourself have never heard of. If he does so, you have lost the advantage and may not get out of it without a few scratches on your own escutcheon. On the other hand, he may be so ignorant as to be impervious to doubt. You will be laughed at. The idea is much more useful if the intention is merely to annoy, and is often used for this purpose by children to teachers. One strong point is the amount of time that can sometimes be wasted merely making clear what is meant. Another is that it undermines authority, since very few teachers can answer this question sensibly. Okay, so 5 plus 4 couldn't be 9 because 7, 8, 9. That's funny. Bro casually turns into Vsauce. I didn't even mean to do that. That's just natural, I guess. Well, I'm sure this guy has a bunch of objections to that statement, but oh well. Okay, but he's saying, like, basically, right, we used associativity to show that 5 plus 4 equals 9. So the question is not whether 5 plus 4 is equal to 9. The question is, can 5 plus 4 be anything other than 9, I think. What is not easy to see is that 5 plus 4 is not 6. I think here is like where things get technical. Like, what exactly is 5? What exactly is 4? And like, why is 5 plus 4? Why can't we just write 5 plus 4 equals 6? When we said that 1 plus 1 equals 2, this meant only that 1 plus 1 was to be called 2. It may perhaps be, for all we know, that 1 plus 1 is really 0, and that we have agreed to call 0 by the name 2, right? And in other words, that 2 is equal to 0. Who can tell? It was agreed that all prejudices and preconceptions about 2 were to be given up. So if we say 0 equals 2, we are hardly saying that none accompany, or that nothing is certain in life. And for example, addition mod 2 satisfies this. Which greatly simplifies and this greatly simplifies all the effort expended in teaching arithmetic. So it remains to be settled whether 1 plus 1 is equal to 0. All we know so far is that it cannot be settled at all if all that is known about the system of numbers is that it is a monoid. Obviously, the thing to do is to assume that there is some universal property. The monoid is universally repelling. So now we're going back to this like weird property of the categories, like with the pointed functions, and like there was only one map or something like that. So basically, okay, if you're in a monoid, you could have 1 plus 1 equals 2, because like this is a monoid, right? Like this is still fine. There's nothing. Sorry, 1 plus 1 equals 0. This isn't. I mean, in addition mod 2, this is not contradictory. This is fine. So we need to assume some extra universal property. It is self-evident that this has reference to the subcategory of the category of all categories. But to obviate any doubt, the morphisms are the functors. Okay. Oh, right. Is this the monoid as defined as a category with one object? Perhaps that's what it means. I'm not really sure what he means when he says this. Oh no, this is pointed with, so it's not, I don't know. The morphisms are the functors. I think maybe we are working um like a monoid is just a category with one object. So maybe we're working in the category of monoids and the functors are just morphisms. They're like homomorphisms, like monoid homomorphisms, something like that. And in that setting, the natural numbers satisfy this like universally repelling uh, property or whatever. Um, let's have a look if he elaborates on this. The reader may well object to the use of monoids and not groups. He should be reminded that this book is not a first text in algebra, and that the difficulties of negative numbers are sufficient unto another section. It must be admitted that monoids are logically prior. Um, so if we have if we basically have, oh no, if S is the monoid with this table, so this isn't actually a addition mod 2 because we have 1 plus 1 equals 1 here. Then the unique monoid homomorphism such that 1 is mapped to alpha satisfies phi of 1 plus 1 equals alpha. If now 1 plus 1 equals 0, then 0 equals phi of 0 equals phi of 1 plus 1 equals alpha, which is a contradiction. Interesting. So I think here he's using the the fact that this monoid homomorphism is unique, and I think right, we're pointed with 1. Right. So 1 has to map to alpha because it's a pointed map, right? Because I think we're taking our base point to be alpha. But because it's a homomorphism and it exists by the universal property, we basically get that phi of 1 plus 1 is equal to alpha, and that means that 1 plus 1 can't be 0 because phi of 0 is 0, which is not alpha. And so the contradiction establishes that 1 plus 1 is not equal to 0. So I think basically he's making the point that if you add this universal property, then you can determine that 1 plus 1 is not equal to 0. But you have to add this extra property. Because if you're just in a monoid, there's nothing stopping 1 plus 1 from being 0. Like, for example, addition mod 2. So I think that's what he's saying. Back in section 1, when the subject of discussion was counting, the phrase natural numbers was mentioned several times. Now that addition is all the rage, the very same phrase has cropped up. Moreover, the set of numbers used has both times been written n0. But is this really legitimate? Is there really such a close relationship between the counting system and the adding system? Granted that many of us are wont to use the same words in ordinary discourse, we might say 1, 2, 3 fiddle-dee-dee as readily as 2 plus 2 is 4. 1, 2, 3 fiddle-dee-dee is funny. Might not this be a convenient shorthand for a situation that is perhaps in reality much more complicated and fraught with difficulty? Okay, I'm just trying to, okay. I think I'm gonna go until we prove the proposition that if you can add, you can count, and then we'll stop there. I feel like that's an appropriate place to stop. So let's continue going for a little bit longer. Question 5. Whether one should count with the same numbers he adds with up to isomorphism. Okay. So should you count with the same numbers that you add with? Okay, let's see. Of course you must use the same numbers in both cases. Sure. When it comes down to practical applications, Despite all this fulfurl about morphisms and whatnot, people count things to see how many they are. Then they put two sets of things alongside one another, and they use addition to see how many they've got altogether. Then they count again to see if the answer came out right. Bring in two separate kinds of numbers, and all that becomes impossibly difficult. Isomorphism has nothing to do whatsoever with it. Ever heard of steamomorphism? That's the place I go to. That's the place I go up to when I want to do some arithmetic. Warm and cozy. Not at all like up to isomorphism. Okay. It is far beneath. I like how he doesn't even he doesn't even respond to the substance. He just responds to the end. Talking to himself, by the way. It is far beneath us to meddle with what anyone finds convenient to do when he is counting or adding. All we want is for everybody to be happy. That's wholesome, at least, I guess. Mathematicians have the sort of orderly minds that want the right tool for the job. It is certainly very unmathematical to count with one and the same system that is used for adding. It is like using this very same screwdriver for putting both screws in and for pulling them out. And mark my words, serious trouble is going to come when you run into transfinite numbers. I like how he says, mark my words. I really find that funny. Reply to objection 2. If anyone is superstitious, he may count with finite ordinals and count with finite cardinals. It is possible to avoid encountering those transfinite numbers by resolutely not counting or adding or anything at all, but just counting and adding pure and simple. Interesting. I don't really... he may count with finite ordinals and finite cardinals. Okay. So this is more just like a superstition thing. I don't know. By resolutely not counting or adding anything at all, but just counting and adding pure and simple. Interesting. I don't really understand that last bit of the reply to objection 2, but I'll move on. If you use a number for several different purposes, who can blame it for becoming a little suspicious? It'll begin to resent such treatment, especially in these days of bloody-mindedness and continual unrest. We must guard against the development of system consciousness among numbers. There is the ever-present danger that they will begin to ask themselves, Was sind und was sollen wir zahlen? Perhaps all numbers will desire to be perfect, or at least prime, or even transfinite. Be kind but firm to your numbers. Write them on paper that is neither too fine nor too coarse. Do not let them get together in large sets. And above all, give them a sense of identification with one specific job. This is the... That has got to be like the most schizo passage in a mathematics book of all time. Oh my word. That is the craziest thing I've ever read in a maths book. Reply to objection 3. Some people seem to like bringing politics into mathematics. There is really nothing to fear from these radicals. If all the partially ordered sets of the universe should one day become discrete, thus discarding their chains, new structures could be manufactured on demand. Okay. Okay. I answer that one may count with the very same numbers he adds with. Okay, let's see. Let's see this proof. If you can add, you can count. That's okay. Proof. In counting with the additive monoid n0, we start at 0. After saying n, we say n plus 1. The few diehards still around who prefer to begin counting at 1 instead of 0 make the adjustment for once and go along with the growing trend, because it will be much more convenient in the present instance to start at 0. That's an answer straight to you, copyright. Thus, we already have a counting system. Okay. So he's saying that the counting system n maps to n plus 1 gives you a counting system. But having a counting system is not enough. What you must have in order to assure success in all your counting endeavors is a real true initial counting system. So let this be any counting system, then the set of all functions from x to x is easily verified to be a monoid. Thus there is, since adding is one thing we feel absolutely confident about and could do blindfolded with our hands tied behind our backs, a unique monoid homomorphism from n0 to the monoid h, sending 1 to f, where f is this function here, which is written n maps to f composed with itself n times. Now it is possible to define a mapping by writing n maps to fn of x. Oh, sorry, yeah, okay, from n0 into x now. Okay. We could go on to show that this mapping is the only morphism of counting systems. This would complete the proof that you can count with the same numbers that you add with. In fact, the very same set can serve for both counting and adding. The qualifying phrase up to isomorphism is not strictly necessary, but some of us consider it a virtue to specify which among isomorphic systems is in use, only when it is absolutely necessary, and to be as vague as possible as often as possible. This is a feeling that merges into the psychological. When two mathematicians discuss the natural numbers, do they both in mind have the same numbers, or are there two distinct but isomorphic systems? It is not the sort of question to ask very often, but perhaps one may be admitted to ask a question once in, say, a sidereal decade. Okay. Let's see, what's his final? Okay. So, I think he's proven that if you can add, you can count, and his proof seems to be that this mapping n maps to n plus 1 defines a counting system, right? Where this is defined because we can add. And he's saying, okay, this is not enough, but you can show that it's universally repelling. And he's saying the map which sends the number 1 to f defines a mapping from n0 to x, which is indeed the unique and only morphism of counting systems from n0 to x. And so therefore we have a universally repelling counting system purely using addition. I imagine this is like a categorical version of like saying the piano axioms allow you to count, or something like this. Like the successor function allows you to count. But yeah, I think I'll stop reading here. I think this is a good place to stop. We've just shown that if we can add, we can count. And I don't know, what's everyone's thoughts on the book? Does everyone want to continue reading this book? We've only just started. I mean, if this is only section 2 of chapter 1, like we've only just started. Alvaro123dy says my brain is fried. Yeah, you and me both. Something I don't get is that if he's saying 1 plus 1 equals 2 by definition, and by this monoid axiom, it cannot be anything else, what is the point of Principia Mathematica proving 1 plus 1 equals 2? I don't know. Maybe Principia Mathematica, I feel like he assumed some axioms or something. I don't know. Maybe Principia Mathematica, I don't even know. It's beyond me. I'm sure there were like steps in that proof that that you can like pick apart and ask way more questions about. But yeah, whatever. Okay. All right, we'll continue for sure. I'm trying to think of like how often to continue. Well, we'll figure it out. Okay, but we'll definitely continue. This seems to be quite. This is like a fun book. This is like the type of book that you can read on stream because it's quite fun. Like it's not that terse and full of like dense definitions and stuff. Um, so yeah, okay. Um, we'll continue with this book for sure. Um, but yeah, okay. I'm going to leave you guys be. Hopefully, this has given you something to ponder about the foundations of mathematics, um, and just generally, just about arithmetic. Next time you do 1 plus 1, you're going to be deeping like, wait, can I do this? Like, is this possible? But yeah. So hopefully you guys enjoyed, and I'll see you guys soon. Um, but yeah, he assumes Peano's axiom. Oh, okay, that makes sense. Yeah, okay, that makes sense. Yeah. But anyway, all right, guys, I'll see you all soon enough. Have a good one.